Here we go, on to 2.7. How do forces relate to energy and momentum? Our objectives: understand the nature of work, calculate work done on an object by a force, and use the work done to describe the change in the object's motion. Understand the nature of impulse. Calculate impulse applied to an object by a force, and use the impulse applied to describe the change in an object's motion. There's some pages for you, but you know. All right, vocabulary preview. Work is not the work where you have to go and clock in and then flip some hamburgers. Work is energy given to or taken from a system by a force. Another way for you to think about another way for you to think about work is just the transfer of energy. Symbol capital W. For the symbol, it's important for you to recognize that it is a capital. So what I do to differentiate my W's, like, is that capital W or lowercase w? That's weight, right? My work, capital W, will have these little wings to it. You may find that useful if your handwriting is half as bad as mine. Just a little strategy for you. All right, the units. If work is the transfer of energy, then it's going to have the same units as energy, the joule, capital J. Basic equation is just work equals force times distance. Impulse is momentum given to or taken from a system by a force. The symbol for momentum is delta P, the change in momentum. It can also be capital J for momentum. I want you to be familiar with both because I use both. So, delta P or capital J. The units are a Newton times a meter or kilogram times meters per second squared. That one's a lot easier because it's mass times velocity, right? Kilogram times meter per second squared. Basic equation is impulse equals force times time. The work-energy theorem says a force takes a distance to give or take energy, kinetic energy specifically. But you can use this with whichever energy. So when a force is applied to an object, the force can do two things, both at the same time. It can give energy from the object, or it can take energy from the object, or the system that the object is a part of. So it can add energy into a system, or it can take energy from a system. It can add energy to an object, or it can take energy from an object. Either one of those. Now, the amount of energy given or taken is called work. Okay, so that's the first thing. Next, the other job that a force does is it's going to give or take momentum from the object or the system that the object is a part of. The amount of momentum given or taken is called impulse. Work is a transfer of energy. Misconception says work is measured in joules, then work must be another form of energy, like kinetic energy, or potential energy, or thermal energy, or chemical energy. No! Work is a transfer of energy from one object or system to another. Work is not something an object has, gains, or loses. Work is the gain or loss of energy by transfer. Work is measured in joules just like all forms of energy, but work is not a form of energy. Because energy is conserved, if an object or system gains energy, then the energy was transferred to the object or system. Likewise, if an object or system loses energy, then the energy was transferred away from the object or system to something else. When a force is responsible for this transfer, then the amount of energy transferred is work. Work is not a form of energy. Work is a transfer of energy. I think you get it now. I think. Let's see about calculating. A force does not always do work. For a force to do work, the force must act while the object is moving, undergoing displacement. So if I am pushing on this microphone with some force, the force is not doing work because the microphone is not moving. It has to also be in a direction parallel to motion, which means the same or the opposite direction the object is moving. So if I do move the microphone this time and I'm pushing down, that force is still doing no work because I'm pushing down while the object is moving this way. So I would say the angle between these two is 90 degrees. It's perpendicular. So if it's perpendicular or anything else, then we're going to deal with all that stuff later. Let me stop right there. We'll deal with angles soon enough. If a force F acts while an object undergoes displacement, then the work is calculated by the equation work equals force times displacement, as long as force and displacement are parallel. Work can either be positive or negative. Work is positive if the force is in the same direction as displacement, meaning the object gains energy, right? Because force, mass, acceleration, it's going to increase its kinetic energy. Work is negative if the force is opposite the displacement, meaning the object loses energy. So here's another way to think about, do I have positive work or negative work? Let's say we have our box, right? And this box is on a surface. And we start applying some force F in this direction, and the box moves this displacement. Okay? So now my displacement is in this direction, and my force is in this direction. What's the angle difference between them? Well, if force is to the right and my displacement is to the right, the angle difference, the change in that angle, is just 0. So that means positive work is being done. They're in the same direction. If I change my force and I say, okay, now I'm going to apply a force this direction, well, now our force is to the left while displacement is to the right. Not to scale. Please don't worry about the size of these vectors. So now I have an angle difference of 180 degrees. Well, there's a math word to describe 180 degrees. Obtuse. Obtuse means anything greater than 90. And if that angle difference between force and displacement is greater than 90, that is obtuse. And if we have obtuse, then we have negative work. Negative work. If the angle difference is less than or equal to 90, then we have an acute angle, and that is positive. Acute is acute, right? Acute, cute, that sounds like positive stuff to me. So things are going to get trickier in this situation where we have a box and we're applying a force at an angle. In that case, we have to take into account the components, which one is actually doing work. And it's only going to be the piece that is parallel that will be doing work. So using trigonometry, you would solve for this side, and then that is the force that is doing the work. We're going to deal with that later on.